Today we're working on lesson 6.3 over conditional probability. So your learning target for this lesson is to find and use conditional probabilities. The way we're going to measure your success is if you can explain the meaning of conditional probability, if you can find conditional probabilities, and if you can make decisions using those conditional probabilities. So the first thing we want to do is just understand conditional probability. So the probability that event B occurs given that event A has occurred is called the conditional probability. And so the way we write that is probability of B given A. So this little line right here just means given. So the way we can think about it is it's the probability that B happens given that A has already happened. You can use sample spaces and two-way tables to find conditional probabilities. So for example 1, we're going to use a sample space to find a conditional probability. A family has 2 dogs. Okay. A family has 2 dogs and 2 cats. They randomly select a pet to get brushed and then randomly select a different pet to get a treat. Find the probability that they select a cat to get a treat given that they select a dog to get brushed. So the way we're going to do this is we're going to first find the sample space. So they randomly select a pet to get brushed first. So we've got dog 1, dog 2, cat 1, and cat 2. And then they randomly select a pet to get a treat after they pick the pet to get brushed. So we have, after dog 1, we could have dog 2, cat 1, or cat 2. After dog 2, we could have dog 1, cat 1, or cat 2. After cat 1, we could have dog 1, dog 2, or cat 2. And then after cat 2, we could have dog 1, dog 2, or cat 1. So that is my sample space. So I'm going to rewrite my sample space. So we've got dog 1. I'll use a little subscript here. Dog 1, dog 2, dog 1, cat 1, dog 1, cat 2. We have dog 2, dog 1, dog 2, cat 1, dog 2, cat 2. Cat 1, dog 1, cat 1, dog 2, cat 1, cat 2. And then finally we have cat 2, dog 1, cat 2, dog 2, and cat 2, cat 1. Alright, so find the probability that they select a cat to get a treat. So probability of picking a cat second, given that they choose a dog to get brushed, so a dog first. Looking in the sample space, we're going to find all the outcomes where you have a dog first and a cat second. So that's going to be right here, right here, these two, and that's it. So there is 4 outcomes where you choose a dog first and a cat second out of a total of how many dog first? So we have 1, 2, 3, 4, 5, 6. because we only care about the given that there's a dog first. So we only care about the total number of outcomes where the dog is chosen first. Okay, and then we simplify just like before, so divide by 2. That's going to be 2 over 3, or if we want to write it as a decimal, 0.667, or about 66.7%. All right, the other way we can do this is by using a two-way table. So a quality control inspector checks for defective parts. The two-way table shows the results. Find each probability. So part A is the probability that you have a pass given it is defective. So the way we're going to find this is we're going to find the number of defective parts that passed over the given, which is the total number of defective parts. So the number of defective parts that passed is right here. So we have 3 over the total number of defective parts is 3 plus 36, so 39. And then we simplify. So we divide both by 3. That equals 1 over 13. Or if we want to write it as a decimal, that's about 0.077, or about 7.7%. All right, part B. Let me label that. Part B, the probability that they failed given that they were non-defective. So the number of non-defective parts that failed divided by our given, the total number of non-defective parts. So here, the number of non-defective parts that failed, we're going to look in non-defective fail, that's right here, 11, over the total number of non-defective. So we're adding everything in the non-defective row. 450 plus 11 is 461. If we want to simplify that, or not simplify, it's already as simplified as it can be, but we can make it a decimal, which would be about 0.024, or we can make it a percentage, about 2.4%. All right, pause the video and take about 4 to 5 minutes to work on these two self-assessment problems. All right, let's check number 1. In example 1, what is the probability that they select a dog to get a treat given that they selected a dog to get brushed? So the probability that they select a dog second, given that they already selected a dog first. So let's look back at example 1. How many of these have a dog second? So we have this one, or a dog for both actually. We have this one and this one, just 2. So there's 2 where we have a dog chosen both times. over the total times a dog was chosen first. So I'm going to look back at example 1 and see how many times a dog was chosen first, and that's this 3 and 6. So 2 over 6. We simplify down to be, divide by 2, to be 1 over 3. Or we can write it as a decimal, about 0.333, or about 33.3%. All right, number 2, in example 2, find A, the probability that a non-defective part passes. So probability that it passes given it's non-defective. So we're going to find the number of parts that are non-defective and passed over the given total number of non-defective parts. So in example 2, number of parts that are non-defective and passed, right here, 450, over the total number of non-defective parts, that's this whole thing right here, 461. If we want to write that as a decimal, that's about 0.976, or about 97.6%. Okay, part B, the probability that a defective part fails. So the probability that it fails, given that it is defective. So we're going to find the number of parts that are defective and failed over the given total number of defective parts. So parts that are defective and failed, that's this number right here, 36, over total number of defective parts, that's 36 plus 3, so 39. We're going to simplify this fraction by dividing by 3. So 12 over 13. And then we're going to convert it to a decimal, which would be about 0.923, or 92.3%. So the key idea for two events A and B, the conditional probability of the second event given the first event is the probability that both events occur divided by the probability of the first event. So we already kind of worked through this formula. So probability of B given A is the probability that they both occur divided by the probability that the given one occurs. All right, so example 3, find the probability in example 2A using the formula for conditional probability. So the way we're going to do this is we're actually going to find our joint and marginal relative frequencies. So we're going to make our two-way table again. You've got your pass and your fail, and your defective and your non-defective. And then remember, we want to have a space for our totals. So the first thing we want to do is figure out the number of total parts. So looking back, if I add 3 plus 36 plus 450 plus 11, that's going to be 39 plus 461, which is 500. So I'm dividing everything by 500. And I did the same thing that I did in the last lesson, and I made this too small. Okay. So passing and defective, we've got 3, and then fail and defective is 36. Oh my goodness. 3, 36. Non-defective, we have 450 and 11. So we're going to find these as decimals, and I'm going to cheat again. I'm going to use the book, but you would do 3 divided by 500 and get 0.006. 36 divided by 500, 0.072. 450 divided by 500, 0.9. And 11 divided by 500, 0.022. For our totals, we're just going to add those. So 0.006 plus 0.072 is 0.078. 0.9 plus 0.022 is 0.922. 0.006 plus 0.9 is 0.906. And then 0.072 plus 0.022 is 0.094. And then if we add our rows or our columns, we would get that the total is 1. All right, so now using the formula, probability of B given A is the probability of B and A over the probability of A. For this one, the probability of B and A for part 2A is pass and defective so we're looking here at 0.006 over the probability of A, which is the probability that it is defective, which we would look at our total for defective, 0.078. And then we can simplify this. So we don't ever want decimals in a fraction. So what I'll do, I'll just move my decimal place over 3 times for both of these. So I'll have 6 over 78. Simplify that by dividing both by 2 and get 3 over, oh, nope, I can divide both by 6, actually. Let's do that. Divide both by 6 and get 1 over 13, which I can rewrite as a decimal, 0.077, or about 7.7%. Which we already found it. This is just another way to find it. So if you have the joint or marginal relative frequencies, or joint and marginal relative frequencies, then you can also just use those. All right, self-assessment. Try both 3 and 4. Pause the video for about 6 minutes. All right, number 3, we're checking. Example 2B is the probability that it fails given that it's non-defective. So probability that it fails given that it's non-defective. So we want to find the probability that it fails and is non-defective over the probability that is non-defective. So looking at my table, the probability that it fails and is non-defective is right here, 0.022, over the probability that it is non-defective is this total for non-defective, 0.922. We're going to move our decimal place over 3 times. So we'll have 22 over 922. We can divide both of those by 2 and make our fraction 11 over 461. Or we can write it as a decimal, about 0.024 or 2.4%. All right, number 4, you study survival statistics of adults from the Titanic shipwreck. The two-way table shows the joint and marginal relative frequencies. Find and compare the probability that they were female given they did not survive, and the probability that they were female given they survived. So we're first going to find the probability that they're female given that they did not survive. So we'll say N. So I'm going to say F, M, S, and N. All right, so we need to find the probability that they're female and did not survive given the probability that they did not survive. So female and did not survive is right here, 0.052, over not surviving total is 0.691. I'm going to go ahead and write this as a decimal since we're going to compare. It's going to make it a little easier. So this is going to be 0.075 or about 7.5%. Okay, then we're going to find the probability that they're female given that they did survive. So we need to find the probability that they're female and survived over the probability that they survived. So female and survived is here, 0.149, over the probability that they survived, the total here, 0.309, write that as a decimal, and that's going to be about 0.482 or about 48.2%. So comparing these two, the probability that they're female given that they did not survive is super low compared to the probability that they're female given they did survive. So we can just say the probability that they were female given they did not survive is far less than the probability that they were female given they did survive. And I know that's a lot to write, so I will give you all a second to copy that down if you don't already have your comparison written. Okay, pause if you need to, but I'm going to move on. My next example, example 4, finding conditional probabilities. At a school, 60% of students buy a school lunch, 18% of students buy a dessert, and 10% of students buy a lunch and a dessert. Part A, what is the probability that a student who buys lunch also buys dessert? So we're saying the probability that they buy, we'll shorten that, they buy a dessert given that they bought a lunch. So probability that they bought a dessert and a lunch over the probability they bought a lunch. So lunch and dessert, 10%. We're going to rewrite that as a decimal, 0.1. Okay, probability that they bought a lunch, that's 60%, write that as a decimal, 0.6. Simplify those, so move your decimal place over one time on both, 1 over 6. Or write it as a decimal, 0.167, or as a percent, about 16.7%. All right, part B. What is the probability that a student who buys dessert also buys lunch? So the opposite way, the probability that they bought a lunch given that they bought a dessert. So we want to find the probability that they bought a lunch and dessert given the probability they bought a dessert. So same thing on first, that 10% or 0.1. But now the probability they bought a dessert is 18% or 0.18. We're going to rewrite this, so move your decimal place over 2 times. On the top, that means it'll be a 10 over 18. Simplify, so I'm going to divide both by 2 and get 5 over 9. And then just in case, we'll rewrite it as a decimal. So 5 divided by 9 is about 0.556, or as a percent, that's 55.6%. All right, for the self-assessment, try number 5 on your own. Take about 5 to 6 minutes. All right, let's check number 5, A through C. At a coffee shop, 80% of customers order coffee, 15% of customers order coffee and a bagel, and 20% of customers order coffee and a sandwich. So part A, what is the probability that a customer who orders coffee also orders a bagel? So we're talking bagel given they ordered coffee. So I want to find the probability that they ordered a bagel and coffee over the probability that they ordered coffee. So bagel and coffee, that's 15%, 0.15, over just coffee is 80%, 0.8. We can rewrite that as 15 over 80, which we can simplify down by dividing by, I think, 5. So 3 over 16, which we can rewrite as a decimal. 3 divided by 16 is 0.1875, or about 18.75%. All right, part B. What is the probability that a customer who orders coffee also orders a sandwich? So the probability that they order a sandwich given they ordered a coffee. So probability that they ordered a sandwich and a coffee given the probability they ordered a coffee. So sandwich and coffee is 20%. Over coffee is 80%. We can rewrite that as 2 over 8 and simplify down to be 1 over 4, which is 0.25 or 25%. All right, and then finally part C, what information do you need to find the probability that a customer who orders a bagel also orders a coffee? So this would be the probability that they order a coffee given they order a bagel, which we would need to know coffee and bagel over bagel. Well, we have coffee and bagel, but we don't have just bagel. So we would need to know the probability. Actually, let's reword that. We would need to know the percent of customers who ordered a bagel. That is what we're missing from that formula. All right, our last example, example 5, using conditional probabilities to make a decision. A jogger wants to burn a certain number of calories during her workout. She maps out 3 possible jogging routes. Before each workout, she randomly selects a route. Afterward, she uses a fitness tracker to determine whether she reaches her goal. The table shows her data. Which route should she use from now on? So what we're going to do for this example is we are going to make a two-way table that shows the joint and marginal relative frequencies. So first thing I want to do is I want to count these tallies. So for A reaches goal, we have 11. B reaches goal, 11. C reaches goal, we have 12. A does not is 6, 4, and then 6. Total, if I add all these, 11 plus 11 plus 12 plus 6 plus 4 plus 6 is 50. So we're going to write our two-way table. We're going to say reaches goal, does not reach goal, and then we're going to say route A, B, and C. And then we always have our total on the ends. So for A and reaches goal, I'm going to take 11 divided by 50 and get 0.22. For A and does not reach goal, that's 6 divided by 50, 0.12. B reaches goal, 11 divided by 50 is also 0.22. B and does not, 4 divided by 50 is 0.08. C and reaches is 12 divided by 50, which is 0.24. C and does not reach goal is 6 divided by 50, which is 0.12. If we add our totals, so my rows, I'll have 0.34, 0.30, 0.36. If I add my columns, I'll have 0.68 and 0.32, and then remember that's always 1. And then we want to find the conditional probabilities for all the routes if she reaches her goal. So we're going to find the probability that she reaches her goal given that she's taking route A, the probability that she reaches her goal given that she's taking route B, and probability that she reaches given she's taking route C. Because we're going to find which route she's having the most luck with. So for our first one, that's probability that she reaches her goal and is on route A, given that she's on route A. So reaches and A, that's 0.22, over route A, that's 0.34. Which we would find is about 0.647. Next, probability that she reaches her goal given that it's route B. So reaches and B given B. So reaches and B, it's 0.22. Over the total amount of B's, Come on, man. That's 0.30. Oh, here. Let me highlight there too. Okay, and that is about the decimal. So 0.22 divided by 0.30 is about 0.733. And then finally, the probability she reaches and is en route C, given that she's en route C, so reaches and is on C, 0.24, given that she's en route C, 0.36. Find that decimal, which is about 0.667. So her best bet here is going to be root B. So her probability of reaching her goal is best on root B. All right, I'll give you just a couple more seconds. All right. The last thing I want you to do is work this self-assessment problem by yourself. I get that these take a little longer. So take about 7 to 8 minutes to work on number 6. All right, let's check number 6. So again, the first thing I want to do is count my tally. So I have 9, 12, 11, 6, 8, and 7. Total. So if I add 9 plus 12 plus 11 plus 6 plus 8 plus 7, I have 53. So in my table, we've got exceed and met expectations. We've got A, B, and C. So for A, that's 9 over 53, which is 0.170. For A, meeting expectations, that's 6 over 53, which is 0.113. For B, 12 over 53 is 0.226. And then 8 over 53 is 0.151. For C, 11 over 53 is 0.208. And then 7 over 53 is 0.132. We're going to add, so 0.170 plus 0.113 is 0.283. 0.226 plus 0.151 is 0.377. 0.208 plus 0.132 is 0.34. Then we add our columns, so 0.170 plus 0.226 plus 0.208 is 0.604. And then 0.113 plus 0.151 plus 0.132 is 0.396. And then we always have our 1 there for our total. All right, so now we want to find which employee should be offered the promotion. So basically we're finding which employee exceeded expectations the most. So the probability that they exceeded given who they are. So we'll do exceeded given A, B, and C. All right, so exceeded and was employee A is 0.170 over the total for employee was 0.283, which if I simplify 0.170 divided by 0.283 is about 0.601. All right, B exceeded 0.226 over all of B is 0.377. So 0.226 divided by 0.377 is about 0.599. And then employee C exceeded 0.208 over their total 0.34. So 0.208 divided by 0.34 is about 0.612. So it looks like employee C exceeded expectations the most. So we'll say employee C should get the promotion because the probability of them exceeding expectations is the highest. And that is it for 6.3.